Hello, welcome back to Piers Rocks. Today we're going to switch between ROM images at runtime. The Software Defined Retro ROM has provided the ability to switch between different ROM images at boot time since day one, but I've now added the ability to switch between different ROM images at runtime without any impact on the running system other than serving a new ROM image. I've got the character ROM of this C64 replaced with a Software Defined Retro ROM, and I've got some of the jumper pins broken out to a breadboard in front of me. So if I'm nostalgic for the bygone days of the VIC-20, at a push of a button I can switch to the VIC-20 character set or back to the Commodore 64. Or if the Apple II was my thing, I can switch to the Apple II character set dynamically. Or maybe I'm a Spectrum guy. And of course this works with any supported system like this VIC-20 that has a different character set chip select line configuration. Just have a different bank of images configured on your Software Defined Retro ROM, and you can use it as a character ROM on that system as well, and you can switch between the images just as you did before at runtime. But I think this is my favourite of all the different character sets I've shown you. It looks pretty rocking on the VIC-20 with its really wide character spacing. And if switching those jumpers by hand gets a bit much, or you want to have the case on your computer, then just add this tiny little daughter board and it will switch automatically. So how's it done? Very similar to the multiple ROM socket support that I showed last week. I'm making use of the two new pins on hardware revision F onwards of the Software Defined Retro ROM and using those as bank switching jumpers. You've got two pins there, so you've got up to 4 different banks you can switch between while the system is running. And the STM microcontroller is preloading all 4 of those images into RAM, and then these two pins are used to switch between the 4 different images that are residing in RAM. If we take a look at the schematic, we have pins 0 to 13 remain the 14 address and chip select lines for the type of ROM that we're actually emulating. We've then got the X1 and X2 pins at the end. What the STM Micro is doing is it's got a 64K image now loaded into RAM, 16K for each of the ROM images it's serving, and it's using the status of these additional X1 and X2 pins as an extra bit into the lookup into the image that it has stored in RAM. So if they're set to 0, it selects from one image. If they're set to 1, it selects from a different image. This is all entirely transparent to the STM microcontroller. It has no idea that these pins have been set to 0 or 1. It's just loading the 16-bit address port from the hardware register and using that as an offset into the ROM table sitting in RAM. That begs the question of how am I doing the automatic switching that's going on behind me? Now, the obvious way of doing this would be to connect another microcontroller to these two new hardware pins and have that microcontroller pull its GPIOs high and low to select the appropriate image bank. That's really just the automatic way of doing what I was doing with the buttons exposed in front of me, pulling the GPIOs, pulling these header pins high and low. What I'm doing here, though, is I've connected a tiny little daughter board to the programming pins here. These are SWD, serial wire debug programming pins that expose the full debug port capability in the ARM processor in this STM32. And this gives you full access to the flash, the RAM, and the hardware registers on the STM32 microcontroller. So what I'm doing in this example is I'm actually changing the pull up, pull down resistor state on these two pins within the STM32 by changing its hardware registers through the debug port. So it is magically and without its knowledge selecting different image banks. But you could equally use this same technique to go in and change one of the images that's sitting in RAM, perhaps one of the inactive RAM images, and then switch to that once it's fully written. I'll go over this particular daughter board that I'm using in a future video. This is the configuration file format required for image bank support. You define sets of images and you can have up to 4 banks in a particular set. Sets are selected using the standard image select jumpers on the system and are loaded up at boot time. And then within that, the individual banks are selected using the X1 and X2 pins. So you can see I've just got an extra setting in here to specify the bank number, and then everything else is the same. This is for the VIC-20 character ROM chip select settings. You can see both CS1 and CS2 are active low here, and then a config file is just pulling down the appropriate images from Zimmers or from GitHub, wherever I've found them. In other software-defined retro ROM news, I've had the first confirmed sighting of a software-defined retro ROM in the wild. So this picture was from David. Thank you, David, for sending this to me. He had 10 boards manufactured by JLC PCB, so they did all of the component assembly for him for a grand total of $60 US for 10 boards, including sales tax, including shipping. So that's $6 per board. And David, I hope you're not watching this. You could probably have got it slightly cheaper, maybe up to $1 cheaper per board, if you'd gone counterintuitively for a slightly more powerful STM32 F4 micro. Some of the more powerful ones are actually cheaper on the lcsc.com, which is JLC's component arm. But David's really happy because he's used this to replace his kernel ROM on his VIC-20. He was previously using a solution that had a separate EEPROM plugged into an adapter board, and it was sitting too proud for him to close his VIC-20 case. Now David can finally close his VIC-20 and he's got a fully working system thanks to the software-defined retro ROM. It's also the first confirmation I've had that it works on any NTSC machine. David's VIC-20 is an NTSC VIC-20, so I've now uploaded, with David's help, a default set of images for the NTSC VIC-20. Now I do have a new hardware revision in the works, hardware revision G. Don't worry, don't panic if you've already got one of the earlier revisions or you're having them manufactured. There's going to be no particular functional changes between revision F and revision G, but I have taken the slightly painful decision to put on a slightly different layout debug port on the software-defined retro ROM, so it's compatible with some other microcontroller boards, so programmers can more easily be used between different platforms. I'll stick that in the GitHub project as soon as I've completed the layout. Before I've had them manufactured and tested them, obviously they'll be unverified. Obviously people are going ahead and manufacturing the unverified revision F. I haven't got any revision F boards yet. They're obviously on the slow boat from China to me. As part of introducing the multiple ROM socket support that I talked about last week, I had to implement a new ROM byte serving algorithm B, and over the last week I've made some improvements to that and done some testing of it compared to my original algorithm A, and I've seen significant outperformance with this new algorithm B. The technical details behind it I'll go into in a future video, but for now it means that any of the individual ROM images for PETs, VIC-20s and Commodore 64s can be served by the cheapest STM32F4 microcontroller, the F401, which has a clock speed of 84 megahertz. Just one slight caveat: all of my testing has been done with PAL systems. I don't have any NTSC machines. If you have an NTSC machine and you're able to test the minimum clock speeds for various systems, I'd love to hear the results that you find. But you can see here that for the Commodore 64, I needed to clock the STM32 at 79 megahertz as opposed to the 84 max clock speed of the lowest end variant to get it to work. Now, when serving multi-ROM sets, actually the algorithm is slightly more complicated, is slightly different, and requires a higher clock speed processor. For serving on the Commodore 64, you'd need to move up to an F411. The F411 is probably the best bang for your buck that you'll get right now from places like LCSC and JLC PCB. As I say, if you're able to test software-defined retro ROM on other systems, particularly ones with other video systems, but also non-Commodore systems, which I don't have, please do that and send me through the results. If you'd like to find out how you can configure the different algorithm to be used, that's all documented here, but I'm happy if you reach out and contact me directly to explain that. I hope you found the dynamic image switching capability of the software-defined retro ROM interesting and useful. I got what I think are some really interesting things coming up on the channel. I've had a number of people suggest that I compare my hand-rolled assembler main loop of the Software Defined Retro ROM with the best that the compiler can offer. I spent a bunch of my time yesterday digging through that, and the findings were quite interesting, so I think I'll do a video on that shortly. Secondly, I got a bunch of different STM32F4 clones that I want to try out and compare to the stock STM32 parts. I've got parts from Gigadevices and Gihi, and I may have them from another manufacturer, I think Artery as well. So that's coming up. And then thirdly, I'm going to cover this tiny little daughter board that I'm using to control a software-defined retro ROM. So if any of those sound interesting to you, please do stick around. Till next time, rock on.